And I suppose I'm looking at both current trends and also where things are likely to head in the future. And because this is a manufacturing course, I will be focusing mainly on the manufacturing and technology sides of things. But I've also tried to broaden it out a little bit and look at some of the other sort of big trends that are taking place within the photovoltaics area as a whole. Now, if I fall flat on my face partway through the talk, it's because I like to wander a bit and I'm bound to get caught in all these leads. So just don't laugh, okay? So the basic areas that I will cover in terms of looking at the trends in photovoltaics are outlined here, and I'll just progressively move through these one by one. So to start with, looking at trends in actual photovoltaic manufacturing, this is a really hot topic for this industry at the moment. And it's because in recent years there has been a very clear trend towards most of the world's manufacturing taking place in Asia, and in particular in China. And so if you look at this particular graph here, which you may or may not be able to see depending on how far you are from the front, but here we're looking at the percentage of total production on the vertical axis. So obviously it's normalised to 100%. So what this is really telling us is the market share for the different countries that are dominating in photovoltaic manufacturing. And not too surprisingly, the green area represents the combination of China and Taiwan. And so you can see that the green area back 10 years ago was basically non-existent, and in the last 5 or so years has become totally dominant in terms of photovoltaic manufacturing. And at the same time, you can see that Japan, that used to very much dominate the world's manufacturing, that's the light blue, seems to have shrunk down to almost nothing. And Europe, down the bottom here, back 5 years ago was very dominant internationally and now has also shrunk down to a very small percentage. And so that's led to a lot of very interesting debate internationally about the whole role of China in particular in terms of their contribution to photovoltaics. And as you can imagine, there's arguments being placed in both directions. Some seeing that what China's doing is absolutely fantastic because it's having enormous benefits in terms of improving the technology and driving down the prices of manufacturing. And yet on the other hand, you can imagine countries like the USA that are wanting to develop their own manufacturing technology, that seeing China being so successful is causing significant problems for manufacturers, particularly in the Western world, that are finding it very, very difficult to compete. And so at the top here, you can see over the last 5 years, this is listing the top 5 manufacturers in the world in terms of manufacturing volumes. And so if you go back about 5 or 6 years ago, that was when the first Chinese company started to have an impact internationally. And that was when Suntech here firstly entered into the top 5 manufacturers in the world. And the other manufacturers are scattered from around the world. You have a European company, an American company, a Japanese company, here's another Japanese company, and then here's Suntech. And since that time, you'll notice that not only has Suntech grown at a very rapid rate to the point where now the largest manufacturer in the world, but other Chinese companies have been established and grown very, very rapidly to the point where now 4 of the 5 companies here are Chinese companies. So Yingli, another Chinese company, JA Solar and Trina, both Chinese companies. And so that's led to this situation where international manufacturing is being totally dominated by the Chinese. And so a reaction of the US has been to slap trade tariffs onto the Chinese companies. And there's a range of reasons why they believe that that's appropriate to do so, and I'm not going to enter into that part of the debate today. There's plenty of discussion in the media about the rights and wrongs of imposing trade tariffs. But it's been very interesting that the impact that it's had, because the Chinese companies have simply got companies from other countries to therefore manufacture the product for them and still ship it to the US. And it's only pushed the price up 2 cents per watt by doing that. And of course that's adding a bit of extra profit along the way by the middlemen in another country that are doing the manufacturing for the Chinese companies. So it's been a very interesting outcome that it's made almost no difference to the price of product in the US or the volume coming in from Asian countries. It has simply meant that the Chinese companies can no longer manufacture the product in their own plant, because otherwise they're being hit with a tariff of something in the range of 30% to 250%. But if they get another company in another country to make the identical product for them, then the way it works is there's no tariff imposed on them, and they can ship their product into the US basically at the same price. Now, on the positive side, we have the situation where China in the last 5 years has really helped drive down the costs. So much so that the prices have reduced by 80% in the last 4 years. And that's a very, very important development for an industry where photovoltaics has long been seen as this magical, brilliant technology, but the problem being just way too expensive for people to use. And so this huge impact that the Chinese and other Asian countries have had in driving down this price, many people see as being one of the best things that could happen to this planet, because this is a technology that many see as being not only the solution for our environment and solving pollution problems, but also for humanitarian reasons, with about 2 billion people in the world not even having access to electricity at the moment, and this being seen as the ideal technology for providing electricity into the developing world, which is the key indicator of quality of life. The other very interesting thing that often gets overlooked, and that is that although the photovoltaic manufacturing is taking place in China, that actually only contributes a relatively small component to the actual final system cost in photovoltaics. In fact, just to highlight that, this will sound quite extreme, but it's the reality of it. To take a silicon wafer and turn it into a solar cell will typically take a Chinese company, it'll cost them round about 15 cents per watt, right? 15 cents per watt. And yet the final system cost for a photovoltaic system installed on a rooftop in the United States is about $4.40 per watt. So the actual contribution of the Chinese in turning a silicon wafer into a good quality solar cell is only an insignificant part of the total cost of putting in a photovoltaic system. And the reality is 80% of the jobs in the photovoltaic industry are downstream. What that means is not within the photovoltaic manufacturing or module manufacturing parts, but downstream. It's in more the, the system design, system installations, all the, downstream marketing, etc., quality control side of things. Okay, so moving on then to looking at price and market trends. These, of course, are going to be impacted by the fact that the costs are coming down so rapidly. And so, perhaps not surprisingly, we have photovoltaics as the fastest growing industry worldwide for its size. It's now a $100 billion a year industry, so it's becoming quite a sizable industry and growing faster than any other industry. You'll all be aware that in 2008 there was a world crisis with a big financial downturn, and then again in 2010, 2011, a lot more concerns about the financial crisis. And you'll notice how the photovoltaic industry has continued to boom right through that period of time. So 2008 there was huge growth, through into 2009 huge growth, and in 2010 we had the fastest growth ever, where the industry grew by 100% in 1 year. And so although most industries in the world suffered quite severe downturns, and many countries were in recession, we saw the photovoltaic industry very much immune from that. And there's several reasons for that. One, of course, is the fact that the Chinese were managing to drive down the price so much that the technology was becoming more and more attractive for more and more people to be using. There are other reasons, of course, as well, and that is the fact that this is seen as being an industry that is so important to the world that when there was a financial downturn, many countries still retained their emphasis and the importance being placed on the use of this technology. And so you saw when a lot of countries were making cutbacks in a lot of areas, they tended not to make cutbacks in this particular area. Oh, actually, one other comment before moving on. We were talking about the market share and the fact that the Chinese are totally dominating market share. We need to put that perhaps a little bit better into perspective, and that's something that this graph does that you wouldn't have picked up in the last one. Now, this is giving you the same information, but it is giving you the information now as a function of the total manufacturing volume. And so the contribution of the Chinese and Taiwanese are the red and orange, which look the same anyway, so you just see it as this bar here. And as expected, you can see it massively growing over the last 5 years. But what I want you to notice is that the manufacturing in other areas has also been increasing. It's not that what the Chinese has done has wiped out industry in other countries. What you'll see is that if we look, for instance, at Japan, that in the other graph looked like, their industry was being shrunk to nothing. It's not actually the case. The yellow here, you'll notice, is still growing every year and has its largest manufacturing volume in the most recent times. Similarly, if you look at Europe, the blue, you can see how the blue segment is actually growing. The point is, it's not growing as fast as the Chinese. But then again, you wouldn't expect it to. It's the Chinese that have been able to drive down the costs and are therefore getting the benefit of a lot of the expansion in the market, which after all is what they are facilitating. They're the ones driving down the cost, enabling the market to grow so rapidly. And so I think that puts quite a different perspective on how you look at the role of the Chinese in this whole scenario. Now, it may sound like I'm spending a fair bit of time talking about this, but it's actually become a very important issue internationally because the Chinese are playing such an important role in the commercialisation of technology, in driving down the costs, and it's become a hot political debate in many countries. I was even asked to go down to Canberra several weeks ago to give a presentation to the Prime Minister's office and the Minister for Energy, and the topic they specifically wanted me to talk on was, is China a threat or an opportunity? Right? And they were quite serious. They wanted to better understand, what was happening in this industry because they see this as a very important industry for Australia's future. And they wanted to better understand whether what China was doing was causing damage to Australia or was a good thing for Australia. Okay, now the huge reduction in price that's come in the last 5 years has a range of very positive implications as well as, the other side where it's seen as threatening people's manufacturing. And for instance, if you look in Germany, which is the largest market in the world, this is from a report done from the Fraunhofer Institute. The source is given over here. And you'll see that the cost of electricity from photovoltaics is in blue and been coming down quite rapidly over the time frame here is 2007 up to the end of 2011. And you can see the price has been coming down quite rapidly as a result primarily of the way the Chinese have been driving down the cost of photovoltaic product. Now this graph also very nicely shows the retail price of electricity to consumers. So this is what's in competition with each other. And you'll notice, of course, as expected, normal retail electricity prices keep going up. We know that here in Australia, don't we? Our electricity prices just keep going up. And so we've got to the point here during 2011 where the two met. Okay, the two are now equal. And so that shows a very, very important benefit that's being derived from the way the costs of photovoltaic modules are coming down so drastically. And so into a situation now where PV module costs are no longer what are limiting the installation of photovoltaic systems in a lot of countries. There's other things that are now providing the limitations. We find that there's a lot of red tape in a lot of countries. People trying to get approvals, trying to organise electricity supply agreements, just being allowed to connect your photovoltaics to the grid, and when you do, who's going to buy your electricity, what are they going to buy it for, all these other issues, and just other balance of systems issues in general. Balance of systems refers to all the other costs associated with putting a system in. You've got your transportation costs, you've got your tariffs if they exist, you've got your metal frames, the mounting structures, you've got your wiring, you've got your interface electronics to connect your PV panels to the electricity grid or whatever you're connecting them to, etc. They're all called balance of systems costs. And because the PV module prices have come down so much, these balance of systems costs, including all the red tape, have become more and more important. Now, the red tape side of things is a lot worse in some countries than others. There's a lot of countries where it's almost impossible still to connect your PV modules to the grid because you know, the policies just haven't been developed yet to enable that to happen. And even if we look at some of the better developed markets, we find that in the US, you know, I was interviewed by some of the US media a couple of months ago, and they were very concerned because the US, they said, has so much red tape. They're making it very difficult for consumers like you and me to put PV panels on our roof because there's so many approvals and so much red tape to have to work through. And they had these figures that a US system costs $4.40 per watt to install on your roof. That's the cost of the final system, $4.40 per watt. And yet, putting the equivalent system onto a roof in Germany is less than $2.50 a watt. And yet both countries are buying the modules at the same price, which at the moment is round about 80 cents a watt. So the modules are making up quite a small component of the cost, particularly in the case of the US. And so the problem in the US is all this red tape, and that's what's preventing much wider scale use of the technology. Okay, so some of the more implications then of driving down the cost in this way. A study has been done by Applied Materials, Charlie Gay. They're the largest equipment manufacturer for this particular photovoltaic industry. And their study showed that there's now more than 100 countries around the world where photovoltaics are now a lower cost option than fossil fuel generated electricity. So we call that reaching grid parity. And this diagram here shows all the red dots representing those locations where photovoltaics are now a lower cost than fossil fuel generated electricity. Now, one of the important consequences of that is that it reduces the importance of subsidies and feed-in tariffs. Now, subsidies and feed-in tariffs has been very, very important for the development of this industry. And some countries have implemented their subsidies and feed-in tariffs in very, very sensible manners that's really helped encourage the use of the technology, which of course was the intention of the respective governments that introduced the feed-in tariffs and subsidies. But the erratic nature of government policy around the world has been a big contributor to the instability in this industry. I don't know if you're aware, but most manufacturers at the moment are really hurting. Okay, we're in a time where supply is greatly exceeding demand. So the manufacturers, in other words, are producing too much product, there's not enough demand, and that is further pushing a lot of downwards pressure on the prices. And so most manufacturers at the moment are basically not making any money, even losing money. So it's not seen as being a very good time in the industry at the moment. And of course, equipment manufacturers are therefore going to be hurting just as badly because if there's an oversupply, then no one, of course, is wanting to expand their production, so no one wants to buy new equipment, etc. Now, just to highlight, I guess, the erratic nature of government policy, even in Germany, where I think they've had a very sensible approach to feed-in tariffs that's really helped stimulate the development of the industry in a very beneficial way, we can still see some of the problems created by changes in the feed-in tariff. Obviously, they have to change it, right? They introduced a feed-in tariff, 5 or 6 years ago. Just since that time, the cost of photovoltaic panels has come down, as we've seen, by 80%. So obviously, they have to keep reducing the feed-in tariff, and they do this on an annual basis. But at the end of June this year, they had announced that there was going to be another reduction in the feed-in tariff. So of course, what happened in June? In June, we had record demand for photovoltaic modules in Germany. And so this is a press release, just a recent one, saying Germany installs record 4.3 gigawatts of photovoltaic solar energy in the first half of this year. And if you read the fine print, you find out that just about all of that was in June. Right? So you get this incredible situation where you get these amazing booms in demand where every manufacturer can sell everything that they can make, and then a month later, they can't sell anything. Right? And these situations are very damaging to the industry. Now, people want to blame the manufacturers for installing excess capacity that's led to the oversupply situation at the moment. And I'm sure the manufacturers are somewhat to blame for the present situation. Everyone wants to increase market share, everyone wants to be the biggest, etc. But I think there's more to it than that. And that is the fact that because of the erratic nature of government policy, and our policy here in Australia is probably as erratic as anywhere in the world, you can very quickly go from a boom situation to a bust situation. The trouble is the manufacturers don't want to miss out on the boom situations. So they want to always make sure that they are producing enough product or have the capacity to produce enough product to meet a boom in demand if it comes, like it came in June. And here in Australia, you know, we had the crazy situation a couple of years ago when the government suddenly in New South Wales here decided to put in a 60 cents per kilowatt hour feed-in tariff, which was way too generous. And everybody knew it was not sustainable. But it was just before an election, not that I'm suggesting there's any link there, but immediately after the election, when the Labor Party lost, Liberal Party came in, they looked at it, they were horrified and said, this is totally unsustainable, we're going to send New South Wales broke, and they instantly axed it. And so we went from having the most generous feed-in tariffs in the world to basically having virtually none. And I see Morgan smiling back there because Morgan's got his own company installing PV systems, and I think Morgan was probably doing really, really well during the time of that feed-in tariff. I'm not going to ask him what happened when the feed-in tariff was axed, but I know Morgan has a very, very good company, and I would recommend Morgan's company to anybody wanting to put PV systems on your roof. But Morgan's not paying me to say that, okay? So government policy has been very important, but we also have to be very, very careful of the implications, because this is widespread. You know, we saw, something like 4 or 5 years ago, we saw the Spanish country implement very generous feed-in tariffs, and it almost instantly grew to being the biggest market in the world. And then a year later, the government there also decided it was sending Spain bankrupt and kind of axed the whole scheme, and it instantly shrunk to being one of the smallest markets in the world. Then we saw Italy having the most generous feed-in tariffs in the world, and now it's in the process of sort of trying to claw all that back. And then we saw Australia do something similar. So, you know, it is a widespread problem, and it is not surprising that we have such an erratic industry for those reasons. And that's why I and many others are very excited about the fact that we are now actually reaching grid parity in a lot of countries, because that will take away a lot of this erratic nature that's created by government policy around the world. You know, we will have a situation where it will simply be normal supply and demand without being interfered with by government policy. And so I think we're going to enter a time over the next probably 3 to 5 years where we'll see the industry settle down a lot with much more stable supply and demand in a way that manufacturers can far better predict what sort of manufacturing capacity that they need to supply their share of the market. Okay, and this is just a press release I thought I'd throw in there because it refers to Australia. So Yingli have done their own analysis. You'll know from the earlier graph that they're the second largest manufacturer in the world. And they've done a study and they've actually concluded that Australia is likely to be the world's first true mass market, driven by photovoltaics now undercutting the price of fossil fuel generated electricity. And you know, they've given some of the reasons for it down here. They say Australia is set to be a world leader in coming years, the result of rising retail electricity prices, and we all know about that, don't we? And falling PV costs, new financing options, which apparently are very effective here in Australia, and a lot of sunshine, which is another real benefit that we have here in Australia. So I don't know about you, I don't know what you're paying for your electricity, but when I looked at my last bill, between 2 p.m. and 8 p.m. each day, I am now paying 52 cents a kilowatt hour. I was quite horrified. The only thing that makes me keep smiling is that I took advantage of those very generous feed-in tariffs that came from when Labor was in policy just before the election, and I'm actually being paid 66 cents a kilowatt hour for what I generate on my roof. So I'm actually very lucky. So I'm not complaining, I actually come out ahead. But there's a lot of people that should be complaining at 52 cents a kilowatt hour. Okay, now there's been a team of experts put together, primarily from Europe, comprises researchers, a lot of manufacturing people, some of the major companies in Europe. And they were put together specifically to try and help the industry understand where things were heading over the next 10 years so that companies, so as people in the marketplace could better prepare for where things were heading in terms of technology, etc., prices. And their conclusion is that prices will keep falling. So we've seen this 80% reduction. These experts believe that the prices will continue to fall from the present level down to under half by 2020. So the prices should keep coming down quite substantially. And they've justified their conclusions. They've pointed to the areas where they see big cost reductions. So the polysilicon feedstock, they see that dropping to half the present price over the next 8 years. And wafer thicknesses, they're expecting wafer thicknesses to keep reducing. In other words, people working out how to make the solar cells of the same efficiency but using a lot less silicon. So again, that helps drive down the cost of the silicon. Kerf losses, that just refers to the amount of powder you lose when you're slicing up the wafers. How much powder do you lose in that process? And again, that loss is expected to come down quite drastically. And another important one is the cost of silver. That's becoming a very important cost in making solar cells because the price of silver has been going up quite rapidly. And solar cells are quite dependent on silver. And so we see a move away from silver that will help bring those prices of silver down. At the moment, silver is the second most expensive material that goes into making a solar cell. And so at the moment, we're somewhere around about the 0.25 grams of silver per solar cell. That's expected to drop down to almost nothing by 2020 because the experts are expecting people will find ways of replacing silver with another suitable metal. That's not as easy as it sounds, but it's something that there is good progress being made in. Okay, so looking then at the application side of things. As the prices come down, you expect applications to change. You can split applications down into three main areas. One is all these rooftop systems, the little grid interconnected systems. And they're the ones that are really dominating around the world now. So they're the ones like houses like this. A lot of them now in Sydney and around New South Wales, thanks to the very generous feed-in tariffs just before the election. And so we're seeing this as the dominant market for photovoltaics now. And that one is expected to really continue to boom, particularly in those countries where grid parity is being reached. And when grid parity is reached, this is the logical way that consumers like you and I are going to be able to easily capitalise on the much lower cost of the technology. Utility scale is a different situation. I'm quite surprised actually to see the way utility applications for photovoltaics are actually developing now. They're still relatively small compared to the rooftop systems, but we are actually seeing some quite large utility scale systems going in, particularly in the United States. The reason I'm surprised is because when you generate electricity in huge systems like this, you're doing it like a centralised power plant, and you then have to distribute the electricity to wherever the houses are or the industry that's going to use it. And so you then have to compete not with the retail price of electricity, but the wholesale price of electricity, which is way, way less. And so I'm not expecting photovoltaics to really compete with fossil fuel generated electricity at wholesale level, probably for close to 10 years from now. It will inevitably happen eventually as the cost of photovoltaics keeps coming down, but I'm not expecting it to happen now. The reason it is happening now is because the governments in the US are offering quite attractive tax credits for people that install photovoltaic systems to generate wholesale electricity in that particular way. And so I've made several trips to the US in recent years, specifically to do with some of the very large installations that are going in there. By large, I mean hundreds of megawatts, right? We're talking about billion-dollar installations. And that's interesting because it means that the companies that are putting in these systems, if you're going to pay $1 billion for a system, you can afford to pay for very, very expensive consultants to come and advise you on, what's the best technology to use, which is the best company to go with, and deal with all the issues associated with putting those systems in. And so it's kind of become almost like a new profession within the photovoltaic industry that's just sprung up in the last year or so, and that is that, very good consultants can now be employed by these big companies to come and advise them on a lot of these really big installations that are going in places like the US. And so for those of you that like the idea of consulting work, I think we have the best students in the world coming from this university here, and I'll give you some good evidence for that a little bit later in this presentation. And so I think people from here have a good opportunity to take on roles like that, where a really good sound understanding of the technology is needed, as well as understanding the use of the technology. Okay, and then the final area here, again, a relatively small application for photovoltaics at the moment, but inevitably these standalone systems, I think, will have to become a huge application for photovoltaics. And I think a very important reason for that is shown in this graph here, because this is showing the average energy consumption per person throughout the world. And not surprisingly, we find that in the US, people consume a huge amount of energy per person. And we in Australia aren't much better. We consume almost as much. We're second highest. Now, experts that have tried to study quality of life have equated energy consumption as being the best measure, the best figure of merit that they've been able to come up with to represent quality of life. And so what we're saying is that US and Australia enjoy the best quality of life in the world, and that the rest of the world, here's the average, way down here. And China, way down here. Well, China's increasing rapidly with the massive economic development taking place there. But there's a lot of developing nations, third world countries, where the energy consumption is very low, and that's because the quality of life there is very, very low. And the obvious way of installing systems in those countries will be little standalone systems like this. People that currently don't even have access to electricity, and that's about 2 billion people in the world. And it only takes a small amount of electricity through little systems like this to make a huge difference, to have a huge impact on their quality of life. Now, the technology has finally become cheap enough that it is easily the lowest cost option now for providing these 2 billion people with electricity. The big question, of course, is, well, who's going to pay for it? Because although it's now clearly the lowest cost option, they still don't have the money to pay for it. But the world as a whole will need to take responsibility for the quality of life for all the people in this world. So one way or another, eventually this has to become an application that becomes huge for photovoltaics. This graph up here shows the world's energy consumption as a function of time. And this is the year 2000, this is the end of the century here. And two very important things I want you to take from this graph. This is done by the German Research Council. There's been quite a few studies like this. They're all fairly similar. This is a fairly well accepted one. Firstly, I want you to notice that the present energy consumption here has to be multiplied by a factor of 4 by the end of the century. And that is simply to take into consideration the fact that the average energy consumption in the world at the moment is so low compared to what countries like in Australia and the US are consuming. Now, because we don't want to significantly reduce our energy consumption, it means that we have to be prepared for the fact that everyone else in the world is going to want to consume more energy. And so the studies have shown that this world's going to need 4 times as much energy within a century. The other important thing is that this yellow section is believed to be the answer, and that's generating the electricity from the sun. That's where photovoltaics comes in. This is seen as being the most attractive option for supplying the world's rapidly growing needs for additional energy. And quite literally, it's not going to be possible for fossil fuels to provide it. Fossil fuels will inevitably start to decline, not increase. So fossil fuels are certainly not going to be an option for supplying the majority of the world's energy needs by the turn of the century. Another option, of course, is nuclear energy. I'm not going to enter into that debate now. There's been a lot of debate on that in recent years, particularly with the catastrophe in Japan. And quite a few countries are now making very firm policies against the use of nuclear energy. But there's still a lot of people very much in favour of using that technology to supply a lot of the world's energy requirements. But you'll notice here in the German study, nuclear basically doesn't even get a mention. I think it's the purple here. You can just see it here. You won't see it down here. So that's a very strong feeling in Germany and in a lot of countries around the world. Okay, so looking at trends in technology. This is what I find particularly interesting, I guess, because that's the area that I work within. And it's been interesting to see how rapidly technology has been developing in recent years. And there's very good reason for that, and that is because, you know, with the industry growing so rapidly and some of the companies growing so large in recent years, it means there's been a lot more funding available to be able to fund R&D. And so we get a lot more of our funding now from industry than we used to. I think the other thing too, though, is that, you know, 20 years ago, not many people really believed that photovoltaics would ever compete with fossil fuel generated electricity. And, you know, I've been in this industry for 30 years, and I must admit 20 years ago, I probably didn't really believe it was possible either. I think it was only probably about 10 to 15 years ago, when we were working on some new technology, that I finally came to the conclusion that it was only a matter of time until photovoltaics would be able to reduce the price to below fossil fuel generated electricity. Now, the dominant technology commercially, and it has been for many, many years, is the screen printing technology. It's a very simple technology. You've learned about that already, so I'm not going to go into a lot of details about the existing screen printing technology. But what I will point out is that DuPont has had a huge impact on the recent developments in screen printing technology. DuPont is a company primarily involved in developing the pastes. And people have always thought that screen printing was a very, very limited technology because firstly, the metal lines had to be very wide, so that was always going to shade too much of the top surface. Secondly, you had to have a very heavily doped emitter because otherwise you wouldn't be able to make good electrical contact to it using the screen printed pastes. So screen printing was seen as being a simple technology, but had a fundamental Achilles heel in terms of the efficiencies you would get out of those types of devices. Now, the work by DuPont has changed a lot of people's thinking about screen printing technology. They're now able to use much more lightly doped emitters than what they used to have. They've developed the pastes that can now contact emitters of, 80 ohms per square. By the time you're up to about 80 ohms per square, you've almost totally eliminated that dead layer that older technology used to have along the top surface. Okay, the dead layer is where, if you dope the surface too heavily, you damage that surface and all the light that gets absorbed within that damaged layer basically doesn't contribute to your electricity generation. And that's mainly the shorter wavelengths of light that get lost as a result of that because they're the ones absorbed right at the top surface. But now that DuPont has developed the pastes able to contact much more lightly doped emitters, a lot of that has changed. And similarly, the newer pastes are able to be printed in a much more narrow configuration than the older pastes as well. So they're able to get a much better aspect ratio. They're narrower and you can also print a higher print. And so that's enabling them to retain the cross-sectional area of the metal lines, but simultaneously reducing the shading losses. So DuPont has made big contributions. And so only a few years ago, typical screen-printed solar cells on Joukowsky wafers were around about 16.5% efficiency. Now they've jumped to about 18.5% efficiency, just thanks to DuPont and those developments that they have made. Selective emitter technology is one that's starting to be evaluated quite widely now for use with screen printing. A lot of companies are reporting results on on selective emitters. There seems to be a bit of a problem though getting that technology into production. Not many companies have really launched into doing large-scale production of a selective emitter screen printing technology. Most of those need some sort of mechanical alignment that makes companies nervous. It makes them nervous about the yields they get, the added complexity of it, the reliability of the equipment needed for forming this more complicated structure. So talking to quite a few companies, they've said similar things, and that is that with all the recent developments by DuPont that I've already mentioned, it takes away a lot of the importance of wanting to go to a selective emitter structure. For those that aren't aware, selective emitter simply means you put heavy doping directly under your metal that solves the contact resistance problem, but you then have lightly doped emitter over the rest of the area, which is where the light penetrates through. But the problem, of course, is that you then have to align your metal to those heavily doped regions. And so manufacturers in general would prefer a self-aligned approach. And what that means is that, yes, you do heavily doped regions because there's clear benefit through having the heavily doped regions in localized areas, but they want a technique where the metal will then be self-aligned to those heavily doped regions to take away all the risk of misalignment and all the associated problems you therefore get with yield. And so in large-scale manufacturing, we're still not seeing a large volume of product produced with selective emitters. The other very important area under development is rear surface passivation. And I suspect rear surface passivation will probably dominate over selective emitters in coming years as being the preferred approach for manufacturers to push up their efficiencies. There's a lot of very good progress being made. The three preferred approaches for passivating the back surface seem to be an aluminium oxide layer capped with silicon nitride. Another one is a thin thermally grown silicon dioxide layer or PECVD deposited silicon dioxide layer capped also with silicon nitride. And then a third option that's being pursued primarily by Centrotherm is silicon oxynitrides as a rear surface passivating layer. So Centrotherm are now offering turnkey systems based on the use of this technology. They're claiming their efficiencies peak at 20%, and they're pretty much guaranteeing an average efficiency of something like 19.5 to 19.6% efficiency. So Centrotherm are doing quite well with that for their rear surface passivation. We're starting to see some companies going into large-scale manufacturing, like REC, for example, are now in large-scale manufacturing with aluminium oxide capped with silicon nitride. And in pilot production, we're seeing some quite impressive efficiencies with several companies now getting to efficiencies in the vicinity of 20%. This is using the standard P-type Czochralski wafers. With regard to rear metallisation, most companies have their preferred approach being based on the use of screen printing of aluminium. In other words, they put down their dielectric passivating layer, they then pattern that dielectric layer, such as with a laser, and then they screen print a lower temperature aluminium paste onto the rear surface that they fire at something like 700 degrees Celsius, and that enables the ohmic contact to be made to the P-type silicon, forms a crude sort of back surface field P+ region in those localized areas, and then in the remainder of the area, the silicon nitride protects the aluminium oxide from that screen-printed aluminium layer. Other approaches here, laser-fired contacts. That's a technology that's been around for at least 10 years now, developed at the Fraunhofer. Does a very good job in the laboratory, does a good job passivating the rear surface. Q-Cells has reported some very good efficiencies there. 20.2% efficiency is using these laser-fired contacts. But I'm not aware of any company that sees it as a production-worthy type of technology. I have spoken to many companies that have said that they looked at the technology and they concluded, for whatever reason, that it wasn't suitable for large-scale manufacturing. And then the other approach is laser doping. So an approach that some companies are very seriously looking at now is that they use a laser not only to pattern the dielectric layer on the back, but to simultaneously dope the silicon to form a localized back surface field region. And if you do that, it then increases the options that you have with how to put the metal on the back. Because if you form your P+ regions in those localized areas, independent of the screen printing alloying process, you can then, if you want to, use a lower temperature metal deposition such as sputtered aluminium or E-beam evaporated aluminium, etc., which then only needs a low temperature sinter. And there's certainly some companies that believe that that low temperature process is very, very important part of getting the best hydrogenation benefits out of the silicon wafers. In fact, we saw some very interesting results at the conference that I've just come to. That's the European PVSEC conference. And on P-type Czochralski, there are now reports of voltages getting close to 700 millivolts by using good hydrogenation in the silicon wafer as a result of avoiding the use of the screen-printed aluminium metal. So that could be something that catches on, or companies may prefer to stick with the very simple screen printing approach. It'll be very interesting to see which way that goes. But I think the fact that P-type Czochralski silicon is now being shown able to get to voltages like 700 millivolts is really astounding a lot of people, and it's really astounding a lot of experts. Because if you look at all the predictions, including that expert team that have been looking at where technology is heading over the next 10 years, they all conclude that the highest voltages that P-type Czochralski will ever get to is in the vicinity of 650 to 660 millivolts. And they conclude that because the silicon quality is just not seen as being good enough, mainly because of boron-oxygen defects. It's not seen as being good enough to get to voltages above that. But some of these latest hydrogenation technology, which incidentally originated from the university here, it's drastically changing that whole perspective. And that by passivating all the boron-oxygen defects, it's now been shown that P-type Czochralski silicon wafers can get to lifetimes of well above a millisecond and is compatible now with achieving device voltages in the vicinity of 700 millivolts. And on the assumption that those voltages are achievable, then the team of experts that concluded P-type Czochralski would never get above about 20% efficiency, you have to rethink all of that. Because if those boron-oxygen defects can be passivated in that way, which we now think is possible, it means that 20% is no longer the ceiling for P-type Czochralski, but rather 23% efficiency. It has that big a difference. So that's something that will be very interesting over the next 5 years to see which direction the industry heads. And I'll come back to that again briefly when I talk about N-type technology. Okay, one final comment here is that efficiency is more important in devices when supply exceeds demand. Now that might be a little bit counterintuitive, but the reason for that is that when demand exceeds supply, it means that the manufacturers who are making the product can sell everything that they make. It doesn't actually matter whether they have particularly good efficiencies or not. They just want to make as much product as they can. That's how they maximise their products and their profits. So when demand exceeds supply, companies don't seem to care too much about wanting to improve their technology or increase their efficiencies. But when times are tough for the manufacturers and supply is exceeding demand, like at the moment, the companies, the cell manufacturers are worrying a lot more about efficiency. And part of that is because in the marketplace, the consumers can now pick and choose. And so the lower efficiency product, they just don't want it because they can get the higher efficiency product and there's an oversupply. And so what a lot of the cell manufacturers are finding is that their lowest efficiency product they can't even sell in times like this because there's an oversupply, some product is not going to get sold, and obviously I guess it's the lower performing product that's not able to be sold. And so at the moment, we have companies placing a lot more importance in trying to improve their cell technology, which is interesting because it's also at the time when they're hurting most and have less money to spend on R&D. Okay, so in this trend towards higher efficiencies, we have these as the 4 leading laboratory technologies. Now there's a big difference between a laboratory technology and turning that into a commercial reality. But these technologies show what's possible. And these are the efficiencies achieved by the 4 leading groups around the world. This graph here is showing historically the record efficiencies at any point in time. So we have efficiency on the vertical axis, time on the horizontal axis, dating right back to 1940 when solar cells were first developed in Bell Laboratories. And all these red diamonds are all world records that were achieved here at this university. And what I'd like to do is point out this one white diamond here And that was from Stanford University. They've always been the toughest competitors with the group here in the photovoltaic area. And that's actually the group from Stanford University that established the company SunPower. You've probably all heard of SunPower. SunPower make a very good product, very high performance commercial product, but they use N-type wafers. So it's a very different type of technology. It's shown in this schematic here. They have all their contacts on the back surface. They have their junction on the back surface. And I guess a distinguishing feature of that technology is not only that it uses N-type silicon, but it has to use the very highest quality silicon, because most of the electron hole pairs are all generated at the top surface, as you would know from your other courses. And so all those electron hole pairs have to travel all the way to the back junction to be collected. And that can only happen if the material is very, very good quality. Otherwise, too many of them will recombine on the way. And so it's a technology that will always be very expensive. Not only are they using very high quality grown ingots, but they can only use a small part of the ingot, because the rest of the ingot, the material isn't a good enough quality. And so the company that's manufacturing the ingots for SunPower end up then having to sell off the rest of the ingot at much lower prices to other companies that are interested in N-type technology. And that company's actually come to us asking us, are we working with any companies with N-type, because they're looking for more companies to be able to sell their leftover N-type material to. Okay, so here's the Uni of New South Wales technology. It's a more conventional structure with a junction at the front surface using P-type wafers. Here we have the Sanyo technology called the HIT cell. Totally different type of technology, where they use an N-type wafer and they use amorphous silicon to passivate both surfaces. And here we have a technology from the ISFH. There is also one other technology that I would have liked to shown here, but I couldn't find a figure of it, and that's the LG Electronics in Korea. They've come up with some very impressive results, also with an interdigitated rear contact device, but it's a hybrid between these two. Again, it's N-type wafers. They use a HIT cell structure, but to produce a rear junction type of device with interdigitated contacts. And I spoke to the LG people at the conference just gone by, because we have a very close relationship with LG. And I congratulated them on the great results they were getting. They've got 23.4% efficiency. So they're ahead of Sanyo with their HIT cell type of imitation technology. And I said to them, well, when will you be scaling that up for production? And the guy goes, oh, no. So they have absolutely no intention of scaling that up for production. The explanation is that it is such a complicated technology that they would not even contemplate scaling that up for production. So they are interested in N-type technology, but they are convinced that it has to be a much simpler technology and one using a far more conventional type of structure. Okay, so in terms of commercialising those high efficiency technologies, I mentioned that it's worlds apart to have a technology in the lab compared to in commercial production. You know, you've got to change a lot about a technology. Demonstrating in the laboratory is very important. That's what shows what works. It shows how you eliminate all the loss mechanisms. But to turn it into a commercial reality is a huge job. And UNSW has tried commercialising its high efficiency pearl structure ever since we developed it, 15, 20 years ago. And several companies have tried and not succeeded particularly well. But the first company to really do a good job with it has been Suntech, and that's the Pluto technology here. So they've been able to take the pearl technology, and they've called it Pluto, but it is this solar cell design. And they've been able to come up with very low-cost ways of implementing that cell design. So in our labs, for this metal here, we use titanium, palladium, silver sandwich. Very, very expensive. So we use titanium initially directly onto the silicon because it's a very low work function metal, gives us a very low contact resistance. It means that we can reduce the metal silicon interface down to a really tiny amount, and reduce down the recombination accordingly. And then we want to put silver on top of it because silver is very, very conductive, 1.6 microohm centimetre. So it's the best conductor. So we want to have silver on top of the titanium. But the trouble is the titanium and the silver interact with each other because of their differing electrochemical potentials. So you can't stick the silver onto the titanium. So then we have to put a passivating metal layer in between, and that's where we use palladium. So we put palladium on top of the titanium, and then we put silver on top of the palladium, and we end up with a solar cell that costs you $1 million to make. It is a great technology, but who would ever buy it? Well, some people will buy it. You know, if you can make the most efficient solar cells in the world, you will find that there are some companies wanting to make cells for their solar cars that are really determined to win. And we've been very lucky that some of these cars have very large budgets. So, for example, Honda was willing to pay us millions of dollars to make these solar cells in our lab for their solar car. And yes, they won the World Solar Challenge. You know, it cost us a huge amount to make these solar cells. And that was probably the first true commercial implementation of this technology. But never again will we sell those solar cells because no one will ever pay the prices. But what Suntech has been able to do is reduce the price of this solar cell by 99%. Right? 99% reduction. And of course you can't do that with titanium, palladium, silver, because it's not just how expensive those metals are, it's the way we used to have to deposit them as well. Very, very complicated to form such narrow strips here where the metal would go and then to form the metallisation. Very, very expensive to do so. Suntech has come up with a very simple, low-cost way of patterning the dielectric. They've developed a great plating technology where they basically use copper for their metallisation. The cost of the copper is way under 1% of the cost of the silver. And so they've been able to come up with the implementation of this cell design in a very simple way that's reduced the cost by 99%, but still allows them to retain most of the high efficiency attributes of that cell technology. And so we've seen in the last couple of years Suntech with lots of press releases about new world record efficiencies for, you know, multicrystalline modules, for P-type Joukowsky wafers, etc. So that's a technology that has done very, very well implementing this Pearl-type structure. Here we have the Sanyo structure. Sanyo themselves put that into large-scale manufacturing and have done very, very well with that particular technology. And then the third of the high-efficiency technologies that's done very well has been the SunPower technology, which came from Stanford University, and that's that rear contact one. So all of these technologies are in production levels of like 0.5 gigawatt or more. So they're 3 high-performance technologies, all in very large-scale production. A fourth one that I'd like to mention is the Yingli technology here, the Panda technology. It's actually, it's happened again. So the Yingli technology is actually, again, based on this cell design, but they've done it with N-type wafers. So they use a boron emitter, and you can see the cell structure here is basically the same as this cell structure here. And Yingli got that technology from ECN in the Netherlands. And Yingli's done a very good job at commercialising that technology and are getting somewhere in the range of 19.5 or even a little bit above. I think their average efficiency is close to 19.5 efficiency with this. So very similar to the Pluto technology in large-scale manufacturing. I think another technology that's done well is the Innovolite technology. And in this case, it was JA Solar, another Chinese company, that recognised the potential of this technology, and they've put that into large-scale manufacturing and I think have several hundred megawatts of manufacturing capacity. And so one of the things I want you to notice from this summary of the high-efficiency technologies that have been successfully commercialised is the leading role that the Chinese companies have taken in doing this. So we have Suntech taking the UNSW technology. We have Innovolite here taking their technology from, JA Solar taking the Innovolite technology from the United States. You have Yingli taking the, one of the leading technologies in Europe from ECN. And one of the things I think the Chinese have done much better than anyone else in the world, and that is that the Chinese companies have looked all around the world to identify which are the best laboratory technologies that they can do a good job commercialising. And then what the Chinese do particularly well is they very efficiently and effectively figure out how to very innovatively turn a laboratory technology into a commercial reality. So Suntech has done that with our Pearl technology from here. JA Sol has done it with the Novolite technology. Yingli's done it with the ECN technology. They're getting the technologies from all around the world. So they're not technologies that the Chinese are actually developing, the laboratory technologies, but they're turning it very effectively into a commercial reality. And Trina, the other big Chinese company, they've linked up with Ceres in Singapore to use their leading technology to try and get that into large-scale manufacturing. Now, the thing that I find interesting is that these technologies coming from these different institutions are made available to everybody, but it's the Chinese companies that are capitalising on them and doing the very innovative development and commercialisation of these technologies. So, for example, in the United States, all the US manufacturers could have used the Novolite technology, but do they? No. And in Europe, all of the European manufacturers could have used the ECN technology, but it took, again, a Chinese company to recognise the potential and do a great job then commercialising the technology. Similarly with our technology from here. You know, uni here would make the technology available to anyone in the world, but again, it's the Chinese companies that have taken the initiative, recognised the potential of the technology and done such a great job with its commercialisation. And it's interesting that when this huge debate commenced, it actually was a couple of years ago, when there's this outcry in the US about all the Chinese product, low-cost product coming into the US. And the US Department of Energy Secretary, Stephen Chu, he is actually an expert in semiconductor physics. He actually has a PhD in semiconductor devices from the US. And he, as the US Department of Energy Secretary, was very concerned over all this discussion taking place. So he personally travelled to China and visited all the leading manufacturers in China to form his own opinion as to why it was that the Chinese companies were exerting such leadership, particularly in manufacturing in the photovoltaic industry. And he came back to the US with a very clear conclusion. He concluded that China was leading the world in photovoltaics not because of low-cost labour or subsidies, but rather because of superior technology. So he had a look at all of this. He looked at what all the Chinese companies were doing. He was looking at how successfully they were commercialising the leading laboratory technologies. And he drew a very clear conclusion about the fact that the Chinese were just doing a better job than the rest of the world at getting the advanced technology into becoming a commercial reality. Okay, so moving on then, I mentioned replacing silver with copper is a key issue for the industry. Okay, there really is a shortage of silver. Photovoltaics has actually been blamed somewhat for pushing the prices of silver up in recent years because the photovoltaic industry has grown so much that we are actually now consuming a significant percentage of the total world's silver consumption. And so this has become an important issue. Now, the team of experts drew conclusions about the fact that basically by 2015, we have to replace a lot of our silver consumption with copper or some other metal. Otherwise, the industry just cannot grow. There just won't be enough silver to allow the industry to keep growing at the rate that it's growing. And so this has become a very important area, not so much because the companies have solutions now, but because they all know they have to find a solution to this particular technology problem. And there's a lot of very good work being done in this particular area. The European conference that I've just come back for, there were quite a few papers looking at this whole issue of, trying to replace silver with copper. And so it's become a focus for many companies now. And one of the very important developments that's happened over the last 6 to 12 months, and that is the company Kuttler is now commercially making available its plating baths. Now, a lot of you may not realise the significance of this. The significance of this is that a very, very good plating technology for plating copper onto the metal contacts of solar cells was developed by Kuttler quite a few years ago. And it was developed as part of the commercialisation by Suntech of the Pluto technology. And Suntech did not want to make that technology of the plating of copper available to its competitors. Suntech wanted to keep that as the technology that gave them a distinct advantage. And so those plating baths, which are a superb product, a superb tool, and do a great job, and we've been lucky, we've had access to the use of those plating baths, but they've never been available to other companies. But that's now changed over the last 6 to 12 months, with so much effort now going into trying to develop plating technology that works well for the plating of copper. Suntech has now decided that there is a gold mine in selling these plating baths to the rest of the world. So these plating baths are now commercially available. The good news for us here is that that now means we can actually get one of those plating baths here on campus. And so I believe that's being shipped at the moment and should be here and operational early next year. So that will be a really good thing for our work here to have such direct access. Prior to this, we've been able to use those plating baths, but we've always had to send our people across to Suntech in China to use the plating baths there. So probably the preferred approach at the moment is to print a seed layer, a very thin seed layer. You can print it by a range of approaches. You can either screen print a seed layer, or you can use inkjet technology, aerosol technology to deposit a thin seed layer that doesn't use much metal, and that provides the interface to the silicon, and then you plate the copper on top of that seed layer. So quite a few companies are looking at that approach, and there's been some good results reported recently. And so that's one direction it could go in. The other direction is just using all plated contacts. And I guess this is our preferred approach here at this university. We've developed some nice technology here that gets used on the Pluto technology. So this shows a schematic of a Pluto cell, and these are all metal plated contacts. And more than 99% of that metal there is copper. So that's our preferred approach, but we've also seen good results from IMAC, Hyundai, Shinsung, UNSW, Suntech, RENA, all presenting good results on all plated contacts. Often people put down nickel initially because nickel, for a range of reasons, is a very good interface to the silicon. But then plate copper on top of that to be the main conductor, because copper actually has pretty much the same conductivity as what silver does. And so this shows you a photograph of two solar cells. Here's one, a standard screen printed solar cell, where you can clearly see the screen printed metal lines. This cell, you'll notice, is much darker. The metal lines are there, you just can't see them because they're plated copper, and by using the technology developed at Suntech, these metal lines are very, very narrow, typically only 25 microns wide, each metal line. So too narrow for you to be able to see here. This shows you a magnification. So this is a cross-section of the copper. So there's 10 microns. So you can see that that width there is about 25 microns. And that's the aspect ratio they get when using these Kuttler plating baths. And then this shows you a magnified photograph of the top surface of the solar cell. So these are those very thin copper metal lines that you can't see here. So this shows you the graph showing how silver consumption has to be reduced. And so this is the graph from that team of experts I mentioned before. And they're I guess, saying that by 2017, we basically have to have eliminated the consumption of silver in our technologies. Okay, so looking at wafer trends. Incidentally, I'll ask you a quick question. I've noticed I was intending to give you a break after about an hour. People like to stretch their legs, go to the toilet, have a drink. I've gone well over the hour. You haven't got restless enough, that's the problem. I can give you a break now for 5 to 10 minutes and then resume, or if you would rather, I'll just keep talking and finish 5 to 10 minutes early. We'll do this the democratic way. Put up your hand if you just want me to keep going so you can go early. Put up your hand if you want a break now. Well, if you want 2 people, you can go and have a bit of a break, but I'll keep talking anyway. So let's push on. We'll look at wafer trends. Now, every year when I give this presentation, Wafer Trends is always an interesting topic because things are always changing in terms of the way the industry is dealing with wafer technology. And there's been a huge change. I was looking over last year's presentation and I noticed the wafer costs this time last year when I gave the presentation was 80 cents a watt. It's now 25 to 28 cents a watt. That's how much the cost of silicon wafers has come down in the last year. That's an enormous change. And that is one of the big contributors as to why the price of photovoltaics is falling so drastically, because that was one of the dominant costs of making a photovoltaic panel. It's now therefore less important to use thinner wafers. I think there will always be a trend towards using thinner wafers, provided you can do so without breaking more of them, and provided you can do so without losing efficiency. Then obviously it's always good to make them thinner. But if you're going to break some of the wafers or your efficiency is going to drop, then a lot of the motivation to go to thinner wafers has now gone, simply because the wafer costs are now so much lower than what they used to be. Now, this is a very interesting topic, N-type wafers. Now, N-type wafers are being predicted to dominate for high efficiency devices. That's a very interesting question. So that team of experts that have been put together to map out the roadmap for photovoltaics over the next 10 years, they firmly believe that for monocrystalline silicon wafers, N-type will gradually dominate over the next 10 years. And there was a very good paper at the European conference I just came from by Stefan Gluntz, a very good paper, and he drew that same conclusion. He thinks it's all heading towards N-type for the high efficiency devices. But Martin Green and I don't agree necessarily that that will be what happens. That structure that they're all thinking will dominate is one that has a rear junction with the interdigitated contacts. And as I mentioned before, that needs the very highest quality silicon. And I know that Martin's feelings on this are that the industry is so focused on driving down costs that a move towards adopting a dominant technology that needs not lower but higher material quality is heading in the wrong direction. He doesn't think that the market will embrace that in any big way. I tend to agree with Martin, and I think there's also other contributing factors that means that N-type for Czochralski silicon wafers won't necessarily dominate. One of those is the fact that I think P-type wafers will do better than what people have expected. See, the main difference is the boron-oxygen defects. The N-type mono doesn't suffer from boron-oxygen defects. P-type Czochralski does, because it's got boron as the dopant. You get oxygen inevitably in the crucible when you're growing the Czochralski wafers. The boron-oxygen defects degrade the quality of the wafer. But I think there's good evidence now that this problem is solvable. So we have developed one technology here that we believe clearly solves the problem. There was another paper, a couple of other papers at the conference that also claim that they've found solutions to the boron-oxygen defects. There's actually been a lot of work done in recent years, some very good work done at Constance University about something like 5 years ago, where they partially came up with a solution to solving or eliminating some of the boron-oxygen defects. So it's an area that people have been focusing on, and if you take away the boron-oxygen defect problem, then there's no reason why P-type Czochralski wafers are not going to get to 700 millivolts. And if you can get to 700 millivolts, then there is no reason to go to N-type technology, because N-type technology is always going to be more complicated than P-type technology. I won't go into the details of that now because time doesn't permit. You can talk more about that if you want within the manufacturing course. But N-type will always be more complicated. Phosphorus has a lower segregation coefficient, which means that as you grow the ingot, you'll get a much bigger range of phosphorus concentration from one end of the ingot to the other end of the ingot. And that automatically leads you to a lot of technology problems when you start trying to make solar cells out of the different wafers in different positions within that ingot. There's other problems also associated with trying to do boron diffusions. It's a tricky process to try and do in large-scale manufacturing. So At the conference, as I mentioned, there was some results. There was a paper by Adel and Sugianto with finished devices close to 690 millivolts. So I think that's caused a lot of people to sit up and take notice of that type of result, because that represents a 10% higher voltage than people thought was going to be possible from P-type Czochralski. And if people can realise that in large-scale manufacturing, then it really does take away a lot of the motivation to go to N-type technology. I think another very important reason also is the fact that N-type will probably never be used for multicrystalline silica wafers in any big way. There's no reason to. When you go to multicrystalline silicon wafers, you don't have the oxygen problem. You're casting the silicon ingot. You don't get a problem with oxygen getting into the molten silicon from the walls of the crucible. There they use a mould made of silicon nitride. So you don't get a boron oxygen problem in general within cast wafers. And so multicrystalline silicon doesn't have the boron oxygen problem. And so there's no advantage to go to N-type technology when dealing with multicrystalline silicon. In fact, quite the converse. If you try and do phosphorus-doped multicrystalline silicon, you get huge problems because of the low segregation coefficient that I mentioned a moment ago. So you produce an ingot and you get such widely varying resistivities for your wafer. In other words, widely varying doping concentrations throughout the ingot as a result of that low segregation coefficient. Also, the boron diffusions tend to need higher temperatures, and the multi-wafers don't respond well to higher temperature processing. So there's a lot of reasons why N-type will probably never be used in any big way for multicrystalline silicon. And this is a graph done by that same team of experts for the International Technology Roadmap in photovoltaics. And the blue diamonds here show the expected market share of N-type for multi-wafers. In other words, they're expecting it to stay basically at 0%. The triangles, on the other hand, in red, represent the expected share of monosilicon wafers that get taken up by N-type technology. And you'll see that at the moment it's down at about 10%, but they're expecting that to increase to around about 2/3. That there represents about 67%. So that's what they're expecting. But in making those conclusions, they haven't allowed for the fact that 700 millivolts is now achievable, because in making these conclusions, these are the efficiencies that they've said that they expect. I keep having this problem, don't I? Too many buttons to push. So if you look at the efficiencies they predict, this is what they're thinking will happen with the N-type mono wafers. At the moment, they're around about the 20 to 21% efficiency. They're expecting that to go up to above 23% efficiency by 2020. On the other hand, if you look at the P-type Czochralski, that's at the moment at something like about 18 to 19%, close to 19%, and it's expected to saturate at around about the 20% level. Now that's something that we know is not appropriate. We know now that P-type Czochralski, with the new passivation technologies for boron oxygen defects, that these are going to go well above that and probably up to these same levels that N-type technology are expected to achieve. So consequently, we don't think this graph will necessarily be the way the industry heads in the future. And when you look at the breakdown then of the wafer types, as shown in this top graph, you'll see that the red triangles, that represents the share from the mono Czochralski wafers. At the moment it's 40%. That team of experts expect that to stay basically constant. And all the rest are the cast wafers. And with the cast wafers, they fit two categories. You get the normal casting process, which at the moment dominates, but that's expected to drop right down and be replaced by a newer technology that I talked quite a bit about in this lecture last year. And that is where you seed the growth of the ingot during the casting process. We call it seeded cast wafers or cast mono wafers. By seeding the casting process, it means that you can actually grow an ingot that is predominantly single crystal silicon, but you can do so without the oxygen that the Czochralski wafers have. So the material that you get from this casting process, shown in these green circles here, that's expected to dominate into the future because it's still lower cost than Czochralski wafers, but it achieves probably at least as good a quality silicon wafer as what the Czochralski is able to do. Okay, now it brings up the topic of thin films. Where do thin films fit into the whole scenario? Question? Okay. Czochralski? Yes, so the red triangles are all Czochralski wafers, combination of N-type plus P-type. These costs here, yeah, they're P-type Czochralski wafers. Yeah, they're the dominant one. If you look at commercial manufacturing at the moment, you know, it's something like 90% of all the silicon wafers are P-type Czochralski wafers.
What are the main factors that drive that cost down in the past years, and why these factors won't apply to high quality?
Well, these wafer costs have been driven down. The main contributors are the actual silicon purification costs is a big component. There is the formation of the ingot, and then there is the wafering. They're the three dominant costs, and it was always the silicon purification that completely dominated those three costs. But the silicon purification costs have been brought down quite drastically in recent years through economies of scale and also improved technology. And also the wafering, we've got new wafering technology, you know, diamond wire sawing, and even before that, wire sawing, replacing the diamond saws. So we're seeing a lot of improvements in technology, we're seeing a lot of economies of scale. And even the casting process is now being able to be done a lot more effectively and at lower cost. So, you know, all those three areas we're seeing big improvements, but we're also seeing a lot of downward pressure because oversupply. So there's a big oversupply at the moment in terms of the silicon wafers. And that is also helping push the price down to values that are probably lower than what are sustainable at the moment. So probably sustainable values here would probably be something more like about 35 cents per watt. But the technology is continuing to improve. So it's only probably 6 to 12 months before these actually become the real sustainable costs for the industry. Yeah? Well, you know, I've always liked float zone wafers, but the reality is that the manufacturers that make the wafers, they've never agreed that float zone can be produced at the same sort of costs as Czochralski. So it's not a technology that's ever taken off, and the advantage of Czochralski over float zone is much, much greater now than it ever used to be because, you know, all the technology development's all gone into the Czochralski and the casting processes, and all the economies of scale are in those areas. So I think it's far less likely now that float zone has a chance of having an impact than what it was 20 years ago. And even 20 years ago, the manufacturers said, no, it's not a cost-effective alternative. So even though you get higher efficiencies, you get higher quality wafers, higher efficiencies, you know, even SunPower will choose to use Czochralski N-type because there's such a big cost differential. And SunPower need the very highest quality of wafers possible. Yes?
Is the price of silicon itself included in that cost?
Yes. So the price of silicon is included within there. Look, if you want more information on that, probably one of the leading companies is GCL. It's a company, a Chinese company listed on the Hong Kong stock market. So they're a publicly listed company, so you can find out all the information about their technology, their costing. They will give you their prices that they sell the silicon at. They'll tell you their wafering prices. They will tell you all of these prices for yourselves. It's all publicly available information now. And they're very much one of the world leaders in terms of helping drive the cost down. Okay. So thin films. I actually think times are tougher now for thin films than they have ever been. When I set up Australia's first solar cell production line in 1980, I was told that what I was doing was pretty much a waste of time, because within 5 years, the wafer-based technology that I was setting up was going to be obsolete because thin films would have taken over. When I got to 1990, when we were doing technology transfers based on our technology developed here at the university, I was told, you're wasting your time because within 10 years, thin films will have taken over. By the time we got to the year 2000, people are then saying, well, in 15 years, thin films might take over. Now we're up to 2012. I don't think people are even brave enough to say in 20 years, thin films will have taken over, because everything is heading in the other direction. We're actually finding silicon wafer-based technologies increasing in market share, and we're seeing continued challenges for thin films trying to get a foothold in the marketplace. One company has done a very good job, and that's First Solar. They were gaining quite a reasonable market share, but even First Solar are now struggling to compete with the much lower prices of silicon modules with that 80% cost reduction that's come in the last 4 years. So First Solar are generating most of their market now by creating the projects themselves and creating their own markets. That's how I read the information now available in their earnings releases. And I think another problem that all the thin film technologies have, and that is their durability. There's been no thin film technology that has proven that it has a good life expectancy and good durability and good stability. There's been no thin film technology shown to be able to survive more than 20 years out in the field. And yet crystalline silicon modules, you know, the modules we made back in 1980, 30 years ago, on Australia's first solar cell production line, they're still working as well today as the day they were made. So the market has confidence in the stability and durability of silicon wafer-based technology. And so it's very, very tough for thin films to try and get well established in the marketplace. There's always some people that want to give it a go. But the trouble is, you know, there's even quite recent durabilities being concerned with some of the latest thin film technologies in the hot environments, like in the desert regions. And that was where thin films were thought to potentially have their best opportunity, was in the low-cost, large-scale implementations of technology in the deserts. And so these latest findings in the last couple of years about stability concerns in these hot environments for thin film technologies, I think is a real dampener. And so we're now seeing the thin film market share starting to shrink again. Okay, so just very briefly to finish off with these last three, trends in encapsulation. There needs to be trends in encapsulation, because what's changed is the fact that we're now seeing encapsulation dominating the costs of making photovoltaic modules. We used to have the cost totally dominated by the wafers, as I mentioned, 80 cents a watt only 12 months ago. Now we're seeing typical costs being 26 cents a watt for the wafer, 14 cents a watt for the Chinese to turn that into, you know, high quality solar cells, but then 34 cents to encapsulate them. Now the encapsulation is very important because it's encapsulation that determines the life expectancy for the module. The solar cells will basically last forever if you keep the moisture, etc., from the metal contacts and stop them corroding. So the encapsulation is what primarily determines the life expectancy. And it's a very conservative industry because the manufacturers have to give a 25-year warranty. So they're very reluctant to change their encapsulation. And yet changes have to take place because the encapsulation is becoming the dominant cost in making photovoltaic module. But bankability is a very important issue here. I don't know if you've heard of it, but the big banks now are taking this industry very seriously. And they're determining which companies they're willing to lend money against the use of their products. So they need to know that if they're going to lend a lot of money to put in a huge PV system, they want to know that that PV system is going to function for as long as it says it will. In other words, to satisfy the 25-year warranties. And so the banks will only lend money on these big projects, and even a lot of smaller projects, if they are happy with the product being used. And so this term bankability comes out. So the leading companies talk about the fact that their product is bankable. And what that means is that if you as a consumer want to go and borrow money against putting in a system from, say, Suntech, then you know that that product is bankable, that the banks will be able to lend you money against the use of that technology for your use. And so when you try and change your technology, the banks don't like it. Any change, the banks don't like it. They recognise that technology needs to keep being developed, keep evolving, but they still don't like it. And they have their whole team of experts there to really thoroughly assess any change in technology. And so when Suntech was introducing its Pluto technology, a superior technology in every way I can think of, higher efficiency, more durable, better thermal performance, in any way you look at, it was a superior technology. But the banks didn't like it. It was a change. And so I had lengthy meetings with banks to try and convince them that the Pluto technology was a safe technology for them to loan money against. Because the banks have these very stringent regimes whereby any change in technology, you have to then have product out in the field for X number of years. It has to be tested by independent authorities, all the data generated and all that data made available to the banks so they can assess over X number of years the performance of the technology. Now that makes it very hard to get a new technology into production, because it's like you put a new technology into production, but you can't sell it to any customers for X number of years until you've satisfied all the requirements of the banks. So the banks recognise there's a problem there, but it is one of the issues that does make it very difficult for manufacturers in particular to change their encapsulation technology, which is something that has a big impact on the durability and life expectancy of the modules. Okay, so when we're looking at trends in encapsulation that need to take place, it's not just bringing the cost down. There's a real environmental push to get rid of lead, which means going to lead-free solders or else finding alternative ways for doing the interconnections, such as glued interconnects. And also, EVA is not a good encapsulant for if you're using a technology that's got a selective emitter. Right? EVA, unfortunately, absorbs a lot of the shorter wavelengths of light. Now, for the older type of technology, that didn't really matter because the solar cells with the dead surface layers didn't respond very well to the short wavelengths of light anyway. But now that the newer technologies are responding much better to the short wavelengths of light, it's very important that improvements take place in EVA, or else alternatives to EVA be found that can transmit the shorter wavelengths of light more effectively, around the 400 nanometers wavelength, but also still not compromise the durability of the modules and still help bring down the cost. So it's not easy to find new encapsulants that satisfy all of those requirements, but it's something that the industry is working very hard at trying to do so. Okay, we're also seeing some new approaches being evaluated, such as the use of a printed circuit board type of approach for forming modules. It's where you kind of use your backing sheet a bit like a printed circuit board, and your solar cells become like components in a printed circuit board, and you kind of like place your solar cells onto the printed circuit board. It's a way of simplifying down the manufacturing, bringing down potentially the costs. Again, it will need to be approached that if it's going to be widely used, it's going to have to deal with all the durability concerns of the banks and consumers, etc. Okay, balance of system costs. Balance of systems costs vary enormously from one country to another, and so it's an area that really needs thorough attention in some countries. And module costs are now only 20 to 30% of the cost of a rooftop system in the United States. So clearly the United States have a big problem there that they have to bring down those balance of systems costs, and a lot of those are to do with government policy and rules and regulations and red tape and getting approvals, etc. In Germany, we have a much more healthy situation as shown here. This is from a report from the Fraunhofer Institute, and you'll notice here that the module costs are shown in the orangey browny colour. You can see how the module costs that used to totally dominate, they're coming right down. This is only to the end of 2011. During 2012, there's been extra large reductions in the module costs, bringing these down quite a bit further. the balance of systems costs have been coming down a little bit, but nowhere near as fast as what the module costs have been coming down. So the balance of systems costs still need attention, even in countries like Germany that are leading the world on the system side of installing these installations. Okay, in other countries, they need to learn from Germany. Germany has done a great job, in a sense, driving this industry, driving the use of the technology. And they've worked out how to greatly reduce or minimise the amount of red tape, make it very easy for consumers to get approvals, and then they are also very efficient at doing the installations. All the technicians there in Germany are very well trained and well experienced at installing these systems. And also German companies are very much leading the world in terms of developing very efficient inverters and advanced electronics for working as an interface between the photovoltaic panels and the electricity grid. Finally, just a very brief comment on the education and training side of things. There's a lot of companies that have an increasing interest in getting training for their staff and engaging in technology transfers, trying to improve the efficiency of their product. And what we're seeing now is that many more institutions around the world are starting to implement more advanced training and even educational programs in the photovoltaic area. It's needed to happen. This is becoming such an important industry and a big industry that there needs to be more educational programs around the world catering for the requirements of this industry. Because up until now, this university has the only degree in the world that specialises in photovoltaic engineering. And it's been in existence now for more than 10 years. And this program generates a lot of the best engineers in the industry. We now have more than 500 students enrolled between the renewable energy degree and the photovoltaic degree here at the university. But we're starting to see other institutions showing more interest in implementing teaching programs in this area. But I guess a very important fact is to look at the impact that students from here are having in this industry around the world. We now have more than 40 former students from here in senior management positions of photovoltaic companies around the world. Just to give you a little bit more insight into it, we have 6 of our former students as CEOs of often quite large PV companies, including the world's largest. And we have 6 vice presidents of technology and 16 CTOs of companies around the world. So certainly in the technology area is an area where students from here tend to often specialise. We have a couple of operational officers, a couple of managing directors of companies, 6 research directors, 5 company directors and 2 directors of centres of excellence. And if you look at the top 10 largest manufacturers in China, what we find is that 8 of those companies have former students from here, either as their present or former people in charge of technology. So we see that here I've listed the ones with stars represent current positions from former students from here. So I guess as an encouragement to you all, if you get through your degree, we know that we attract into this degree the very highest students. We know that because the university is constantly asking us to, in a sense, explain why we attract such a high quality of student into this program. And we also know how high in demand the students from here are if you're willing to travel around the world to take on positions. Now, at the moment, there's not a large manufacturing industry here in Australia, so jobs here in Australia are hard to get in manufacturing. We have very large applications for photovoltaics developing and will continue to develop here in Australia if you're interested in those areas. But if you're mainly interested in the technology side of things, such as becoming a CTO or a vice president of technology of a photovoltaic company, you probably have little choice at this stage but to go overseas. If you do, all I can say is you will be in high demand. Thank you.